So today's speaker is Andy Svesko, who needs no introduction to most of us. Andy graduated from ASU last year, and he's now a postdoc at University College London. Today, he will tell us about his recent work on the thermodynamics of quantum extremal surfaces. Andy?
Great. Thank you for that introduction, Helling. Yeah, so it's great to be here to be giving a talk on a Wednesday seminar. I'm honored and privileged. I wish I could be there in person. But anyways, so today I'm going to tell you about some work I put out back in July with my colleagues Juan Pedraza, Watisia Biesma, and Manis Visser, where we provided a systematic study of the thermodynamics of quantum extremal surfaces, in a particular 2D dilaton theory of gravity. And if there's time, I'm also going to tell you about some work that's forthcoming. We hope to put out in October, where motivated by this work in July, we argue that we can derive a page curve for an eternal ADS black hole using a microcanonical gravitational path integral. So before I get to the main meat and the main results, I want to first provide some history and philosophy that's motivating everything I'm going to talk about today. And everything hinges on a key result from 1970s classical general relativity, which is the observation that the laws of black hole mechanics are formally similar to the laws of thermodynamics. So here I've written down the first mechanical law of a static black hole. This is here on the left-hand side. And formally, it looks very similar to the first law of thermodynamics. And this is apparent when you identify the mass of the black hole with the internal energy, the surface gravity kappa with the temperature, and the area of the event horizon of the black hole with the entropy. And Bekenstein, he took this analogy seriously, and using thought experiments, proposed that black holes should actually have a genuine thermodynamic entropy. And this was later verified by Hawking, who found that black holes radiate at a temperature proportional to this surface gravity. And so this tells us that black holes are genuine thermal systems obeying a set of thermodynamic laws, and it's a jumping off point for a variety of subfields, in particular holography and ADS-CFT, as well as emergent gravity. And any serious candidate theory of quantum gravity is expected to have some sort of microscopic explanation of black hole thermodynamics. Now, there are two important extensions of black hole thermodynamics that will be relevant for us. The first is that black hole entropy adds to the remaining matter entropy of the rest of the universe, and they combine into something called the generalized entropy. And the generalized entropy obeys a second law, and it also modifies the first law I wrote down before, where here this is due to the exterior matter. And the second extension is that gravitational entropy applies to surfaces other than black hole horizons. In particular, you can assign an entropy to the cosmological horizon in de Sitter space, to the Rindler and accelerating horizons in flat space, and more generally to what are called holographic screens.
And a quick question. I don't know much
Yes.
about the thermodynamics of black holes. So because of the equation you showed in the last slide, it made me wonder, like when you compute the change of energy in a thermodynamic system, you also include, particle exchange and pressure exchange. Does exist an analogy for those, energy changes for a black hole?
Yeah, so there's a couple of ways of answering this. So first, okay, so this is an expression for a static black hole. You can also include charge as well as rotation. And for several years, and people still do this, that they kind of interpret this variation of the charge and the variation of the angular momentum. They will sometimes interpret those as kind of like a chemical potential and particle exchange as well as pressure. But most people don't view it that way. There's another way that people think about, at least when it comes to like a changing pressure and volume, and that is using something called extended thermodynamics. But that really only shows up when you consider black holes with the cosmological constant. And this will be something that will be relevant later on, which I'll talk about more later on. But generically, it's the volume of a black hole is ill-defined, but you can define a conjugate variable to the pressure which the pressure is identified with the cosmological constant. And then from there, you can write down an extended set of black hole thermodynamics.
Thank you.
Okay.
Can I ask another one related
Yeah,
to
yeah.
that? So when you compute the entropy for a black hole, do you guys usually what use like the microcanonical ensemble? You count.
Yeah,
You cannot count microstates, but like you can
Oh,
use
yeah,
microcanonical ensembles.
This is a great question. So generally people work in the canonical ensemble. You can define a microcanonical ensemble, and I'll talk about this later. But generally when people, so there's multiple ways of deriving black hole thermodynamics. So actually, this will show up in the next slide. But one way of doing it is working in a path integral, using an on-shell Euclidean path integral, where you're working in the canonical ensemble at a fixed temperature. But you can also define it using a microcanonical ensemble, and that'll be something that's key later on in this talk, as well as hopefully our forthcoming paper.
Awesome. Thank you, man.
Yeah. Right. So the first law, the classical first law, or the mechanical first law, is really a statement about classical gravity, but its thermodynamic interpretation is not. And there's multiple derivations of black hole thermodynamics. As mentioned, you can, one way of doing it is describing an on-shell Euclidean path integral and working in a canonical ensemble. But most derivations of black hole thermodynamics neglect the effect of backreaction, namely the effect of the quantum matter in the background altering the geometry of the black hole. And this leads to a number of puzzles and actually begs the question whether your interpretation of thermodynamics of a black hole is accurate, whether it's valid. So if you want to treat the full problem, if you want to study the whole problem and in principle address these puzzles, then you want to account for backreaction, and this means you have to solve the semi-classical gravitational field equations. So here I've written down the semi-classical Einstein field equations, where on the right-hand side we have the expectation value of the renormalized stress tensor of the matter, the exterior matter, and psi here is typically taken to be the vacuum state of this matter. And solving this equation is notoriously difficult because it requires you to simultaneously determine a dynamical geometry as well as a set of field theory correlators. And I'm not going to get into the whole history of studying this problem as well as the validity of studying this problem. But the point is that the picture is somewhat incomplete if you don't include backreaction. And the reason why this matters, for example, is suppose you want to determine what ensemble you're working in black hole thermodynamics. That typically requires that you have to extremize a thermodynamic potential, like the Helmholtz free energy, with respect to the background, which means you need to have a detailed knowledge of the geometry as well as the quantum state. And that means you have to be able to solve the semi-classical field equations. Okay. Now, there's another puzzle, which is related to the problem of backreaction. And it's well known, as I'm sure many of you are familiar with. It's the black hole information puzzle, which essentially boils down to, does the quantum state of Hawking radiation evolve unitarily? And very recently, this question garnered a lot of excitement because it's been argued that the Hawking radiation, or the entropy due to Hawking radiation, can be computed using what's known as the QES formula, which I've written here, which is essentially, it's the extremization of the generalized entropy as a function of this surface X, where X is a codimension 2 surface, which is called the quantum extremal surface, or the QES. And we'll take as a definition that a QES is the codimension 2 surface which extremizes the generalized entropy. This is how it's normally described in the literature. And it's in fact a variant of the QES formula, known as the island formula, that computes the Hawking radiation as a function of time. And it was argued and shown back in 2019 and 2020 that it seems to follow a unitary page curve, which addresses the black hole information puzzle. I'll say more about this later if we have time. So with all that as motivation, the problem of backreaction is difficult to solve in dimensions 4 and greater, but progress can be made if you work with so-called 2D dilaton theories of gravity. And this is because the backreaction can be entirely captured by the Polyakov action. So the main goal of this talk and the main goal of our paper was to study the gravitational thermodynamics, including this backreaction in 2 dimensions, but paying particular attention and with the viewpoint that quantum extremal surfaces may be present and they are of interest. So to briefly outline, first I want to review and then systematically solve. I'll show some of the details, how one solves the so-called semi-classical JT gravity action, where JT gravity is a particular 2D theory of gravity. And we'll see that when you include backreaction, you necessarily find the existence of non-trivial quantum extremal surfaces. From this, we'll then derive a first law of mechanics associated with quantum extremal surfaces. And then, since we've solved the problem of backreaction, we'll be able to study its thermodynamic interpretation. And we'll find that when we work in the microcanonical ensemble, the QES mechanics is equivalent to thermodynamics. And there's multiple highlights along the way, which we can use as kind of checkpoints as we go through this talk. One of the first big results is that when you go through and systematically solve the semi-classical JT gravity problem, you'll find that the gravitational Wald entropy is exactly equal to the generalized entropy. And this includes even time dependence of a von Neumann entropy of a CFT in the background. We'll also see that when we study quantum extremal surfaces, that really we should be studying so-called nested ADS Rindler wedges, which I'll describe what those are. And in fact, we're really going to be studying the mechanics and thermodynamics of these nested wedges. But then in the microcanonical ensemble, the mechanics and thermodynamics of these wedges become the thermodynamics of quantum extremal surfaces. And then lastly, if there's time, with essentially our setup, we can use the QES formula to derive a page curve for the eternal black hole. Okay, so that's essentially the main outline. And now I'm just gonna go to town. But if you have questions along the way, do ask.
So can I just ask,
Yes.
what's the page curve for an eternal black hole?
Oh, very good. So, so I will show it later, but essentially, so there's different ways of describing the eternal system, but essentially what we're gonna mean is we're gonna have an eternal black hole that will allow to radiate in a flat space region. And then you imagine dropping in matter such that it maintains its mass, so that the black hole entropy always stays the same. But then even with this, since the black hole is radiating, there will still be an increase of the radiation entropy. And so the page curve, so you're familiar with the page curves that goes like a triangle. The page curve for an eternal black hole goes up, it rises linearly in time. It meets this plateau, which is the value of the black hole entropy of the full system.
Oh.
So it goes like this, reaches up and hits a plateau. So, okay. So first I want to kind of motivate why even study a two-dimensional theory of gravity and why JT gravity. And it's essentially because four-dimensional black hole physics is encoded in 2D dilaton gravity. And one way to see this is that you can consider a spherically symmetric, asymptotically flat, charged black hole. And in the near extremal and near horizon limit, the geometry goes like ADS2 cross the 2 sphere, where here in purple is the ADS2 geometry, which I've written in Poincare coordinates. And the length of the ADS2 region is proportional to the charge of the higher dimensional black hole. We can see this pictorially if we use Penrose diagrams. So here on the left-hand side is the Penrose diagram of the near extremal, near horizon charged black hole. And in blue denotes the Penrose diagram for the eternal ADS2 space. And if I were to zoom in on that, this looks like a black hole, like a double-sided black hole. And indeed, the ADS2 space is often called and treated as an eternal ADS2 black hole or a wormhole. And in fact, if I didn't tell you, you might mistake this as Rindler space, Minkowski and Rindler space. And so I'll use interchangeably that the eternal ADS2 black hole really is ADS Rindler space, where this is the right Rindler wedge. Okay, so why dilaton gravity? Well, that's because it comes from a spherical reduction of the action that your charged black hole solution is a solution of. So here's the metric ansatz, where phi here is the dilaton, phi naught is some constant, which I'll describe in a moment. And if you plug this into the Einstein-Maxwell action, perform the usual dimensional reduction, you find with a little bit of work the Jacobi, Teitelbaum, or JT gravity action. So this is the classical gravity action in 2D, which is a non-minimally coupled gravity-dilaton theory. Okay, so with this action, we want to study its classical solutions first, and then we're going to describe or include semi-classical effects.
So what are these two terms?
The two lines?
Yeah.
Yeah, so, right, so all we're doing is you just perform a dimensional reduction, and the Ricci scalar takes a particular form. It gets nominally coupled with the dilaton field here. This 2 over L squared, that just comes from when you dimensionally reduce the F squared, and so there's really a charge in here. So the 2 over L squared is hiding this charge. Then this second term here, this is just the dimensional reduction of the Gibbons-York-Hawking term. And so again, it kind of couples like the couples to the Ricci scalar. I've actually done something else though, where I've actually, though I won't really describe it in too much detail, this extra 1 over L term, that's coming from, I'm including a local counter term because you'll find that certain expressions end up being divergent as you go close to the boundary, the ADS boundary. And so in order to rid yourself of those divergences, you can include a local boundary counter term. And so that's what this extra quantity is.
So K is the extrinsic curvature?
Yep. Yeah, K is the extrinsic curvature of the, really the one-dimensional submanifold in your two-dimensional space.
I see. And then for the treatment of the divergences, normally we renormalize some parameters. And it's not that you are just wanting to get rid of divergences, but you want to absorb them in certain parameters. So I'm a little confused about your comment that this -1 by L is simply to remove divergences.
So we aren't performing any sort of renormalization here. It's more of like, you will find that, so for example, if you compute the entropy, say, or no, not the entropy, say you compute the energy in this system, you'll find that it just blows up. We're not doing any sort of renormalization procedure. It just blows up. And if you want a sensible answer, you typically either do one of two things. You either perform a background subtraction. So you either perform a background subtraction, or you can you can add in a local counter term. And that will also rid yourself of a divergence from a physical quantity. So yeah, so this isn't related to renormalization necessarily. But then people in ADS CFT, they do like local boundary counter terms because that's related to holographic renormalization. But we won't need any of that with what I'm going to discuss. Okay. Assuming Tanmay is satisfied.
Well,
Somewhat.
I mean, no, satisfied is not the word. I mean,
Yeah.
trying to remove my ignorance.
No. So another way to think about it is, so if you recall how the derivation works of black hole thermodynamics with the path integral, you often perform some sort of background subtraction. Or you subtract off the result from the Minkowski space. And that isn't necessarily because you're trying to renormalize the system. It's just, it's because you have an infinite quantity that's not sensible. And so there, you usually perform background subtraction. But you can also opt to use particularly in ADS spaces, you typically opt to include a local counter term.
Okay.
But it won't, I mean, it's hidden in all the expressions I'll write down, but it won't come up too often with what I'll describe. Okay. So we have the classical JT action. Let's first discuss its solutions. The dilaton equation of motion fixes the background to be that of eternal ADS2. So this is just the solution of the dilaton EOM. And so I've written here the metric of the eternal ADS as an eternal black hole, where mu here is a mass parameter because it's proportional to the ADM mass of the system. The gravitational equation of motion, which I've only written down formally, fixes the form of the dilaton. And generically, the dilaton can be time dependent, but we're only going to be interested in time independent solutions for the dilaton. And with the classical model, you can actually go through and use standard techniques to find the standard thermodynamics of the ADS2 black hole. And you find in particular that the entropy or the temperature of the eternal black hole is proportional to the mass parameter, such that in the extremal limit, when the temperature goes to 0, that corresponds to the mass going to 0. And consequently, you find that this constant phi naught is proportional to the entropy of the extremal black hole. Now, m phi here, this is just the ADM mass of the system, and it satisfies a SMAR relation, and it also satisfies a first law. Okay, now all of this was essentially worked out during the mid-90s, the decade of the 90s, essentially, when I was age 0 to 10. And so, one question is, why are people interested in JT gravity again? It was worked out. And it's because more recently, some new insights have been found. And one is that you can exactly quantize the theory using Hamiltonian methods. It also provides a nice, concise example of ADS CFT. More recently, it was shown that you can compute the full Euclidean path integral, including sum over topologies and geometries. And that's because you can show that there's a duality between the Euclidean JT gravity and a particular types of double-scaled matrix models. And so you can perform the Euclidean path integral using these double-scaled matrix model techniques, including finding all non-perturbative corrections. Why it's of interest to us is because the backreaction problem will be exactly solvable. And this was of interest to people a couple years ago because you can address the black hole information problem. Okay.
Can I interrupt? I mean,
yeah.
when you say backreaction is exactly solvable, you mean in the semi-classical approximation?
Yes, so I mean that we'll be able to write down the semi-classical gravitational equations of motion and then exactly solve exactly solve those solutions, exactly solve that equation. So yeah, so it's in, but yeah, you're correct. It's in the semi-classical approximation.
Okay.
Andy, yeah. I don't mean to be pedantic. Just I want to compare. So these all features that you kind of say as positive features for the GT gravity, aren't they also satisfied by Liouville theory? By Liouville.
Yeah, no, exactly. So yes, exactly. So there's a variety. So I could have picked other 2D theories of dilaton gravity to look at, including Liouville theory. And in fact, there are some that are very special, called the RST model or CGHS model. And those are essentially, they're highly related to Liouville theories. So a lot of this stuff was worked out, yes, with Liouville theory, and it was worked out for other models. There are some caveats with why JT gravity is even simpler than those models, which I can get into the details a little bit, but I didn't write down what the actions are for those models.
This, I mean, it's not like, I mean, or in other words, there is many things that people has been done in this JT gravity that can translate to Liouville, or maybe it's the other way around. Many things that done in Liouville have been translated to GT, right? Okay.
Yeah, I agree. I mean, certainly the motivation. Basically, what's nice is that with JT gravity, it exactly fixes your space-time to be ADS2. There's no other solution your geometry can be. It has to be ADS2, which is one simplification that is, particularly helpful when you describe the Euclidean path integral approach, because it has to be, always has to be this ADS2 geometry that you include handles on. Another reason why is because, so there's these certain flat space models called the CGHS model. So there, if you want to study the problem of backreaction and Hawking radiation, you'll find that when you include the Polyakov action, that it doesn't you can no longer solve the system explicitly. What you end up doing is you have to introduce some new term called either the RST term, or you include, or there's another model called the BPP model. And I think something similar happens with the Liouville theory. And basically what it is, you want to maintain what's called the Kruskal gauge symmetry. And if you don't have that, you can no longer solve the problem exactly. But in the case of JT gravity, you don't have to include anything else. So the classical JT action with just adding a Polyakov term, you can still solve everything exactly. So that's another simplification of JT gravity. So that's why we studied this first. Actually, I'm lying. We did study CGHS and RST first, and it's a paper that's coming out next year. But then we realized that some of the equations of motion are more difficult, so we decided to let's go back to JT where people are talking about it more recently. But anyways, thank you for that. That's a very good question, and it also gets to more of the history of these things too. Okay, right. So I want to discuss and describe or include semi-classical effects. So what we're going to do is we're going to include external matter. We're going to represent it by a number of C massless scalar fields. And classically, the energy momentum tensor of these scalar fields is vanishing, but it's famous that quantum mechanically there's a one loop anomaly such that the expectation value of the stress energy tensor is non-zero, and it's proportional to the Ricci scalar of your two-dimensional space. Now it turns out all of this physics can be encoded in the one loop Polyakov action, which I've written here. In the Polyakov action, I've written it in a way so that it looks local. It's typically a non-local action, but you can introduce an auxiliary scalar field, which is a two-dimensional CFT of central charge C. So it entirely encodes all of the physics of the number of C massless scalar fields. And when we set C to 0, that's the classical limit. And so you would be back to the gravitational or the classical JT action.
So why is C going to 0 the classical limit? Why is C going to infinity?
Oh yeah. So no. So C. Yeah. So this is. So really, there's a hidden H bar here. So it's really like C times H bar. And C goes to 0. It eliminates this Polyakov action, and we'll see that it really does act. C goes to 0 acts like a classical limit. The semi-classical limit is related to C goes to infinity, and G goes to 0, where you have G is the 2D gravitational constant. So that's the semi-classical limit. Is C going to infinity? But I can describe that a little bit more in a couple slides if you would like. But C goes to 0 is it's the classical limit for us.
Now physically, C goes to 0. Sorry, C going to 0 is a very weird limit because it's like you don't have degrees of freedom at all.
Yeah, exactly. So basically what it is we're eliminating the influence. So we're just getting rid of all the fields that are on the background, and the C goes to 0 limit. Really, there's secretly some like H bar multiplied by this, and you can view it as the H bar to 0 limit. But
generally, I mean, you have in the path integral, you have this action divided by H bar. So H bar going to 0 is the classical limit.
Mm-hmm.
So that would be.
So that's what you think.
Correspond to the coefficient of the action going to infinity.
Right. So I would say, how should I say it? So actually that's what happens in the path integral, but the action itself is really proportional to H bar times C. So then if you include it in the path integral, those H bars end up canceling, and you're just left with a C term. But again, so I can describe this in more detail in a couple slides if you would like, where you'll see why we define the semi-classical limit in the way we do. Okay, so to describe backreaction, what we mean is we're going to let the expectation value of the stress energy tensor source the gravitational equations of motion, so the classical JT gravity equations. And so here it is symbolically. This is the modified, together this gives you the modified semi-classical gravitational equation of motion for JT gravity. And one important thing here is that notice that the auxiliary field chi and the dilaton don't couple. And so what this tells us is that the dilaton solution doesn't change at all, or the dilaton equation of motion doesn't change. And so that means that the gravity solution that we found before is the same metric we had before. So that means that the eternal ADS2 black hole is unaffected by including this backreaction. This doesn't mean that phi and chi won't depend on backreaction, but it just means we can work with the same black hole. And this is another one of the reasons why JT gravity is particularly simple. Okay. So now I want to spend the next few slides showing some of the details how to solve the semi-classical JT model. This is actually a really great exercise for students who want to study quantum fields in curved space and backreaction. And essentially, the first thing we're going to use is a nice feature of 2D spacetimes, which is that any two-dimensional spacetime is conformally flat, where here y plus and y minus are just null coordinates that I've introduced. This is called working the conformal gauge. And when you substitute this metric, this conformal gauge, into the semi-classical JT equations, you find the following set of equations, where this first one is the equation of motion for the chi field. And it has a very easy formal solution. Chi is just given by the conformal factor in your conformal gauge, plus this C function, which obeys the scalar wave equation. And when you plug this ansatz into the expression for the expectation value of the stress energy tensor, it takes the following form, where here I've introduced this function t plus minus, which is given by a set of derivatives of your C functions. And t plus minus is important because it can fully characterize, or it characterizes the quantum state of your matter, in that the expectation value of the normal ordered stress energy tensor is proportional to this function t plus minus. So this is something that will be of use in a moment. So I could go back to Ptolemy's question. There is something here about the semi-classical limit, which is that, so here we have this parameter g, and inside t plus minus, if I look back here, it's proportional to c. And so what you end up doing is you end up working in the limit where g times c is fixed, but the semi-classical limit is defined so that c goes to infinity. So working in a large C expansion, and g goes to 0. So that's what is defined collectively as the semi-classical limit. The C large to infinity is actually also coming from, if you want to think about it in terms of the spherical reduction, it comes from the fact that you're eliminating ghost-like corrections. So you want to eliminate certain ghost-like corrections that come from the dimensional reduction. And so in that context, you have to look at large C. But then in order to have a systematic and well consistent solution of these equations of motion, you have to work in the limit where g times c is fixed in those limits. Okay. Right. Okay. So this is an important result, which we'll use in a moment. Okay. So to proceed, in order to proceed in solving the problem of backreaction, we already have the solution for the metric, but we still have to find the solutions for chi and phi, and they are state dependent. So that means we have to specify the state in order to continue. So when we're working with eternal black holes, there are generally two states of interest, the Boole-Ware vacuum and the Hartle-Hawking vacuum. And in particular, to describe the Hartle-Hawking vacuum, really describe both of them, you introduce two sets of coordinates, the advanced and retarded static coordinates, little v and u, where the metric takes this following form, or global Kruskal coordinates, capital V and U, where the metric takes this form. The rows are different. And we can define the Hartle-Hawking vacuum state in two ways that are equivalent. The one that's most familiar is that the Hartle-Hawking state is the state such that the expectation value of the normal ordered stress tensor in static coordinates is given by a thermal energy, where the thermal energy is proportional to this Hawking temperature squared. And this is just the typical statement that the Hartle-Hawking vacuum, as seen by an outside static observer, will appear thermal at a temperature that's given by the Hawking temperature. And once you specify these states, you can actually, so you go through and you plug in this consequence into your semi-classical field equations, and you can actually work out what the full differential equation is exactly analytically. So what you find is when you're working with the Hartle-Hawking vacuum, the dilaton is rather simple. It's just a classical solution plus a constant semi-classical contribution given by this. And the auxiliary field chi is a little more complicated, which I've written here in Kruskal coordinates. And these constants Ku, Kv, and K are just integration constants. What's surprising is actually, seemingly in the literature, this solution has never been written down fully, which we were all surprised by. And importantly is that there are as we'll show in a moment, that you can pick these constants, these integration constants, in such a way that this will give us the full von Neumann entropy. You can show that the matter entropy is given by the full von Neumann entropy. And there have been special subsets of this solution that were written in the literature before, where the Ks take a particular form. And importantly, when you do that, you'll find that you get a generalized entropy, but from that generalized entropy, you don't find a quantum extremal surface upon extremizing. But when you use this more general solution, we will find a non-trivial QES. Another thing I want to mention really quickly is that if you were to solve the problem with respect to the Boole-Ware vacuum state, the solutions are somewhat dramatically different. In particular, the dilaton becomes much more complicated. But since we're interested in thermodynamics, we want to have a thermodynamic interpretation, so we're not interested in the Boole-Ware vacuum. So I won't talk about the Boole-Ware vacuum anymore. Okay. So in principle, we've solved the backreaction problem by solving for this JT action by solving the semi-classical gravitational equations of motion. And we've done so, we've found analytic solutions. And so now we're interested in studying the gravitational thermodynamics of our eternal ADS2 black hole. And so what we want to do is we want to compute the entropy. And so the way we're going to do this, we're going to use the so-called gravitational Wald entropy, which is given by, in this case, it's straightforward to calculate. You can show it's given by the classical entropy that I wrote down before, plus a semi-classical contribution, which is solely coming from the Polyakov action. And now since the Wald entropy is given by phi and chi, which are state dependent, it also tells us that the Wald entropy itself is state dependent. And when you work in the Hartle-Hawking state, the Wald entropy is just given by the classical piece that we had before, plus this C/12, which is just coming from the constant semi-classical correction to the dilaton. And then this extra term here, this chi, that's coming from what we had before, which is the semi-classical Wald entropy. And since the Hartle-Hawking state is thermal, we can interpret this gravitational entropy genuinely as a thermodynamic entropy. So for those who aren't familiar, I'm kind of skipping the details of the definition of the Wald entropy. The Wald entropy is a generalization of the Bekenstein-Hawking entropy formula, and it's entirely consistent. So the point is, you can just, if it's helpful, you can just view the Wald entropy as Bekenstein-Hawking entropy. It's just a formula. It's a particular formalism in a way of deriving a gravitational entropy for spacetimes that have bifurcate killing horizons, but for arbitrary theories of gravity. Okay, I won't go into the details of how that works, but if one is interested, I can talk about that for days. Okay, so as mentioned before, is that if you specify the integration constants Ku, Kv, and K in chi, which you can do using these three criterion, you can show that the semi-classical correction to the Wald entropy is exactly equal to a von Neumann entropy of a two-dimensional CFT reduced to, in the vacuum state, reduced to an interval in your curved background. So this is the semi-classical correction to the Wald entropy, and this is the expression, for those who aren't terribly familiar, this is the expression of the von Neumann entropy of a 2D CFT restricted to an interval, where the interval is defined by endpoints U2, V2, and U1, V1, where these are critical coordinates. These deltas are just UV regulators to regulate what happens with the entropy at the endpoints. And so this leads to our first big result or realization, which is that the gravitational Wald entropy with this solution for chi that was seemingly unnoticed in literature can exactly capture the full generalized entropy. And this actually resolves a puzzle from the mid-90s in the flat space models, where it was shown that the Wald entropy seemingly only captures a part of the von Neumann entropy, but with this particular solution, we can find the full generalized entropy, the full von Neumann entropy. And in fact, this calculation I showed here, while I showed it in the case of ADS spaces, it also holds up in the flat space case as well. Also generically, since chi is time dependent, that means the von Neumann entropy is time dependent. But in what follows, we're going to consider the case we're working on a particular time slice where the von Neumann entropy is time independent. Okay, so now that we have a generalized entropy, which is just given by the Wald entropy, motivated by the study of quantum extremal surfaces, let's actually extremise the generalized entropy. And the way we do this is we vary one of the endpoints of your interval and keeping the other side fixed. Then you'll find that there is a quantum extremal surface outside of the horizon of the eternal black hole. So here, this is in short-shield coordinates, this is the radial position in short-shield coordinates of the QES. And this epsilon here is some parameter I've chosen that's small, that's proportional to g times c, such that when c goes to 0, the position of the quantum extremal surface just coincides with the horizon.
Sorry, Randy,
yeah.
what are you extremizing? What is the quantity that you are extremizing?
Yeah, so what you do, you're extremizing. So the way people discuss it is you're extremizing the location and the shape of the quantum extremal surface. So literally what you do is you take you could look at this, for example. This is a function of u and v, and you fix one of the endpoints, say u2, v2, and then you take the derivative with respect to u1 and v1, and that tells you about the location and the shape of the quantum extremal surface. Now, so this is only a semi-classical bit, but you include the gravitational part as well, and that's what gives you this position, which you first write in uv coordinates, but then you can exchange those in terms of short-shield coordinates. So that's all I've done here. Yeah. The fact or the observation that the quantum extremal surface lies outside of the eternal black hole horizon is actually something that was noticed by Almhiri and Maldacena and others back in 2019. But here we've actually included the full effects of the backreaction, whereas they found they didn't necessarily include the effects of backreaction. And one other important point is that the QES actually defines a so-called nested ADS-Rindler wedge that lies inside of the full eternal black hole, where the bifurcation point of this nested ADS-Rindler wedge is given by or is equivalent to the position of the quantum extremal surface. So for a picture, what I mean is that, so here's your full eternal ADS black hole, the two sides. And this green shaded region is the nested ADS-Rindler wedge, because it looks like a ADS-Rindler wedge, where this point here, at this apex here, that's the location of the QES, which coincides with the bifurcation point of this nested ADS region. I'll have more to say about this geometry, including the parameters of alpha in a moment. Okay, so now that we've found that including backreaction within the context of gravitational thermodynamics leads to quantum extremal surfaces, well, we want to study, or we're interested in studying the mechanics and thermodynamics of this quantum extremal surface. In a way, passing the approach of studying black hole thermodynamics, but now to quantum extremal surfaces, which in some sense can be viewed as like a semi-classical generalization of a horizon. That's not quite accurate, but that's kind of what the motivation is. And so what we're going to do is, since we've seen the QES defines a nested ADS-Rindler wedge, what we're first going to do is we're going to work out the mechanics and thermodynamics, including the backreaction of these nested ADS-Rindler wedges. And we do this by first finding or deriving a Smart relation. And then from the Smart relation, we can derive a first law. And then, since we've worked out the backreaction, we'll provide a thermodynamic interpretation of these mechanical laws for ADS-Rindler wedges. And we'll see that when you work in the microcanonical ensemble, that the thermodynamics of the ADS-Rindler wedges should really be interpreted as QES thermodynamics. Okay, so in order to get there, I want to first describe a little bit more of the geometry of this nested wedge. The nested wedge is really the causal domain of a Cauchy sliced sigma that's stretched between the bifurcation point B and a point on the conformal boundary. And to describe the geometry inside of this nested wedge, I'm going to denote coordinates using bars. So the Schwarzschild coordinates inside here are given by r bar and t bar. And this ADS-Rindler wedge is generated by a Killing vector zeta, which is just equal to the Rindler time translations, so dt bar. And we're actually going to be interested in what zeta looks like with respect to the coordinates of the eternal black hole. And so doing a standard calculation, this is what you find. where these f functions are just hyperbolic trigonometric functions. V and u are just the static coordinates. Kappa here is the surface gravity of the horizon of the nested wedge, so not the horizon of the eternal black hole. And this alpha is just a time parameter that's is the distance on this time-like conformal boundary, which separates or is between the point sigma reaching intersecting the boundary and the points where the null surfaces intersect the boundary at these v plus minus. An important thing that we'll use as a consistency check is that when alpha goes to infinity, so when the time interval blows up, what happens with the nested wedge is you can imagine it stretching all the way up here and it pushes all the way back so that it entirely encompasses the eternal black hole. So in other words, alpha goes to infinity limit, the nested wedge becomes or coincides with the eternal black hole. That'll be a useful consistency check as we go along. Okay, so what I want to do in order to derive the mechanics first is I want to first work out the Smart relation. And the reason for this is because the Smart relation is known to relate the various thermodynamic variables. So here I've written down the Smart relation for an ADS black hole, a static ADS black hole, in d dimensions. So m is the mass, a is the area of the black hole horizon. And something that Carlos asked earlier is about the volume and the pressure. This is often interpreted as a volume pressure type term, where lambda gains the interpretation as a pressure, and this volume or this theta is often interpreted as a thermodynamic volume because it's a variable conjugate to a pressure. And we'll see this show up in a moment with our ADS2 services or ADS2 space. Now there's multiple ways of deriving the Smart relation. In my opinion, the best way of doing it, but also can get somewhat bogged down in the details, is using the covariant phase space techniques, which I won't go into detail on what any of those words mean, but if you have any questions, feel free to ask. And then from the Smart relation and using covariant phase space techniques, you essentially vary the Smart relation and you can write down a mechanical first law. So here's the mechanical first law that's associated from basically just performing variations on the Smart relation. This delta H is formally given in terms of what's known as the symplectic current in covariant phase space language. And you can show that delta H is really delta M because H zeta here is the Hamiltonian that's generated or that's due to the generator of zeta, and it's equal to the quasi-local energy, which you can identify as the ADM mass. Okay, so this is just kind of a broad overview, the purpose of Smart relation and the first law. We're going to apply this formalism to the case of semi-classical JT gravity. It requires a slight modification of covariant phase space techniques, where now you have to be careful with what you mean when you work with boundaries. And we're going to consider a Cauchy slice sigma that's evaluated on a particular time slice where the entropy is time independent. And in doing so, following the techniques, you can find the semi-classical Smart relation is given as follows. So this is the semi-classical Smart relation for the nested ADS wedge. And so there's a lot of terms here, so let's kind of go through them. So on the left-hand side, these E zetas are just the quasi-local energies, asymptotic energies. And in the alpha infinity limit, you can show that just these E zetas correspond to the mass of the eternal black hole and a semi-classical correction to this mass. This term here is a quantity that we will recognize in a moment as the generalized entropy. And then we have these two quantities where we've included these theta G and a theta C. And these are simply the moral equivalents to this thermodynamic volume. And we call them killing volumes. In this case, since I've included a counter term, which I mentioned near the top of the slides, this is really a counter term subtracted killing volume, which is of note for people who are interested in extended thermo, because usually in extended thermo, they consider background subtraction to define the volume. But here we've been able to do it using a local counter term. So this is actually a somewhat new result here. In the C to 0 limit, you find that this just coincides with the classical Smart relation for the eternal black hole. And in the alpha infinity limit, this just corresponds to the semi-classical black hole the smart relation for the semi-classical black hole. Okay, so now using covariant phase space techniques, or if you really want, you can try to vary all of these quantities. You'll find that you arrive at the semi-classical smart relation, which is a mechanical first law. This is just the variation of the quasi-local energy, variation of the what we'll see as the generalized entropy. And we have these two extra terms, delta H's, and they're formally given in terms of the integral over the Cauchy slice of the symplectic currents that are relevant. There are actually explicit expressions for these, but they're a bit messy, so I spared you the details. Okay, so this is a semi-classical mechanical first law of nested ADS-Rindler wedges. Okay, but with the classical first law, we now want to try to provide a thermodynamic interpretation, which we can do since we've solved the problem of backreaction. And essentially what this means is we want to know what does a static observer in the nested wedge see the Hartle-Hawking state as. And it turns out a straightforward calculation shows that the expectation value of the normal ordered stress tensor in the static coordinates adapted to the nested wedge is again a thermal energy, but now not at the temperature of the Hawking temperature, but at the temperature what we identify as kappa over 2 pi. Remember, kappa is the surface gravity of the nested wedge. So in other words, a static observer in the nested wedge will see the global Hartle-Hawking state of the eternal black hole as a thermal state, but now at a different temperature. And somewhat serendipitously, this result is because the vacuum states in the nested wedge, as well as for the Hartle-Hawking vacuum in the nested wedge and in the eternal black hole, are actually one and the same. And this was recently shown, a paper was put out a few days before we posted our article, which considered the same question of looking at nested Rindler wedges, but in flat space. And they considered an infinite sequence of nested Rindler wedges. And they found that in flat space that indeed this is the case, where each nested observer will see what is the equivalent of the Hartle-Hawking state as a thermal state, but with respect to their acceleration, so they have a different temperature. So our calculation here is the ADS2 realization of their results.
But the result is in any dimension, because it's in flat space,
yeah,
so you are not restricted to.
No, yeah.
To
I can't remember the full calculation. I think they looked at 2D. They just looked at the 2D model of Rindler in Rindler flat space. They're arguing that it will hold for higher dimensions in general. And I mean, they were looking at, the way they studied the problem is they looked at Bully-Above transformations. They weren't trying to solve the full backreaction, but they used the standard kind of techniques of QFT and curve space and found that the Hartle-Hawking states are always the same.
This is something that May will like to look at.
Yeah. You might.
The
Yeah,
backreaction in flat space.
Yeah.
I mean,
Anyways, right. So with this identification, particularly, we can now justify the identification of the temperature being proportional to kappa, and with that, you can identify the mechanical first law as a genuine thermodynamic first law, where this quantity here is just the generalized entropy. We recognize as the Wald entropy, but we know that the Wald entropy is the generalized entropy, and it's a thermodynamic entropy. This is then just the eternal energy, and these two quantities, they're somewhat mysterious, but you can interpret them as work-like terms because they add negatively to the internal energy. Okay, and this is actually consistent with kind of extended thermodynamics. Though we're not explicitly doing extended thermo. It's just when you go through the calculation of looking at the smart relation and the semi-classical first law, you find that these terms are necessarily there. Okay. So now with the first law of thermodynamics, we want to study its various ensembles, and also, so we want to study its various ensembles. And the way we're going to do that is first we're going to look for the free energy of the system, or the thermodynamic potential, and study its stationarity conditions. And so from the first law, you can identify what the Helmholtz free energy is, because the Helmholtz free energy is the thermodynamic potential which is stationary at fixed temperature. So you can find that if you define the Helmholtz free energy like this, using this first law, you find this such that it's stationary at fixed T. And this defines a canonical ensemble, which is a system that's at fixed temperature. And from the canonical ensemble, you can define a microcanonical ensemble, which is in the standard thermodynamics lore is a system at fixed energy where your thermodynamic potential is given by the microcanonical entropy. And the stationarity condition is then the variation of this microcanonical entropy at fixed energy. And the stationarity conditions, you can find that there's a correspondence between them. And basically the way you get from the canonical to microcanonical ensemble is you perform a Legendre transform on the Helmholtz free energy. And this is true in the standard thermodynamic picture, but it also holds this correspondence in gravitating systems, which is a result found by Brown and York in the early 90s. And so we're going to apply this setup or this correspondence between canonical and microcanonical ensembles to our semi-classical JT action or setup. Then you'll find that the microcanonical ensemble is naturally identified because the microcanonical entropy is given by the generalized entropy, and the microcanonical ensemble is then given by the stationarity condition of the generalized entropy. So this leads to our second big result, which is that the nested wedge thermodynamics is equivalent to QES thermodynamics when we're working in the microcanonical ensemble. And that's because the stationarity condition is effectively extremizing the generalized entropy, which we saw before that when you extremize the full generalized entropy, you get the quantum extremal surface. And so this leads to a somewhat fundamental insight in that when you work in the microcanonical ensemble, it ends up being, in a way, more natural to consider the entropy of quantum extremal surfaces than that of black hole horizons when you include backreaction. And it's simply just due to this observation here. Okay, so this is a first kind of good stopping point. And so I can summarize everything I've shown so far, which is essentially the meat of their big paper we had in July. Essentially, we analytically solved the semi-classical JT action very systematically and found a new solution for the auxiliary field chi. And found that with that solution, you find that the Wald entropy entirely captures the generalized entropy, and that extremization of this generalized entropy leads to a non-trivial quantum extremal surface that lives outside of the eternal black hole horizon. And then from there, we found that QES naturally defines a nested ADS Rindler wedge, from which we derived semi-classical, mechanical, and thermodynamic first laws, and found that when you work at the microcanonical ensemble, these statements transfer to a statement about QES thermodynamics. There's a variety of additional highlights. We did lots of other things which I didn't really discuss, and I can describe them in more detail, or I can move on and discuss what we're going to describe in a paper we're going to put out in the next, hopefully next month. So I'm happy to either stop here, depends on the time, or I can keep going for, don't worry, it's not actually 48 slides. I only have really 5 more slides to talk about the page curve for an eternal black hole. So I'm all ears for who wants what.
Well, if it's just 5 slides, maybe we can maybe 5.
Yeah, I lost the time. What time is it?
You can continue for about 5 to 10 minutes.
Okay, great. I'll yes, I will go quick. Okay, so essentially, now that we've studied the QES and thermodynamics, question is, what do we do with it? Who cares, other than me and a couple other people? And you can use the thermodynamics and what you found to study the information paradox for the case of eternal black holes. So I'm actually going to skip this slide in most of the detail. This is essentially a statement about the information paradox. So what Tommy asked earlier is, what is the page curve for a eternal black hole? To contrast it, this is the page curve of a dynamical black hole, and it follows this curve here. But I'll describe all this in detail in a second, actually, because I'll describe the page curve for an eternal black hole. So essentially, what we're doing is we're going to take an eternal black hole, an ADS black hole, and we're going to glue on flat space regions here. So these green regions are flat space regions. This is the usual eternal black hole. And we're going to allow the system to evaporate. So Hawking radiation will be emitted into the flat space regions and will never come back. But in order to maintain equilibrium, so the black hole doesn't lose mass, you imagine pumping in some matter so that the mass stays the same. So I didn't draw the pumping in the matter here, but that keeps the black hole entropy fixed. And the black hole entropy is the sum of the entropy of the two sides of the black hole. So the entropy of the black hole should always be at twice the Bekenstein-Hawking entropy, which is just this constant line here. Okay, but now, if you are interested in studying the entropy of Hawking radiation as it goes into this this bath region here, this flat space region, what you'll find is that the entropy of Hawking radiation begins to increase, and that's because there's a buildup in correlations for between interior and exterior Hawking modes. And what you'll find is that it follows a roughly linear in time curve. This is known as the Hawking curve. And this leads to a paradox. And the reason is because at some particular time, eventually, the entropy of radiation will exceed that of the entropy of the full system. And this is a paradox because a principle of quantum mechanics is that a fine-grained entropy, which is that of the von Neumann entropy of radiation, should never exceed or is always bounded by the coarse-grained entropy of the system. So in this case, the coarse-grained entropy is the total entropy of the system, which is given by twice the black hole entropy. And at some particular time, the von Neumann entropy will exceed that. And that leads to the paradox in that it seemingly violates unitarity. So if you care about unitarity, and if you want quantum mechanics, if you still want to maintain unitary quantum evolution in the context of QF, quantum fields in a black hole background, then you want your system to obey what's called a page curve after its inventor. And the page curve says that, okay, initially, sure, the entropy will increase, but eventually, in this particular case, it will stabilize and just plateau to this curve here. What happens in the dynamical case is that since the black hole is decreasing in size, the black hole entropy, thermodynamic entropy, will decrease. And so the typical drawing for the page curve for a dynamical black hole is that it should rise, like we saw before, but then it should start decreasing and tracking with the curve of the black hole. So in a dynamical case, the page curve follows like this, and in the eternal case, it follows like this. Okay. So what people got excited the last 2 years in my particular subfield was that they argued that the entropy of Hawking radiation can be computed using the QES formula. Where here I've written the QES formula a little more specifically, particularly to the case of JT gravity, where here's the classical entropy piece. This is the von Neumann entropy, so this is really the extremizing the generalized entropy. And they found that a variant of this formula, known as the island formula, will actually track the Hawking radiation. And the island formula, what it essentially is that it's the special case where you let this sigma x, which is a codimension 1 slice that's bounded by the extremal surface, you allow it to be disconnected in the case of a dynamical black hole, where it's given by the region where radiation is deposited into, plus some other slice known as the island, where the quantum extremal surface is the boundary of this island. And the claim is that when you include this island, as I'll show in a moment, that you can receive corrections to the Hawking curve such that you get this flat piece, and that together you can derive the page curve. So how it works, we can apply our setup. Essentially, first consider the scenario where there is no island. Then you're interested in the region of interest is the Hawking radiation entering these flat space regions, where we consider the flat space or the sigma x to be the sum of these two intervals here that extends from the boundary to this point just outside of the conformal boundary, and this slice as well. So the radiation region is just these two slices. Since we're working in the flat space region, there's no gravitational effects, so the dilaton is set to 0. And then the QES formula instructs us to extremize just the von Neumann entropy, because remember, when you exclude the dilaton, you're getting rid of this piece, so now you're only extremizing this contribution. And when you do that, you find that the radiation entropy due to these regions gives you a linear in time curve. So this is the standard Hawking calculation. We find that the radiation entropy increases linearly with time. And so if this is all you had, then you would find a paradox that I mentioned before. Now, if you include an island region, things change. So now the region of interest, this sigma x, is given by the same regions we had before with sigma rad, plus an island, which is this slice here between QL and QR, which is the quantum extremal surface. And then when you plug this, so since we're including an island, we're working inside of the gravitational region. So we have to include the dilaton. And when you do this and you now extremize the generalized entropy, you can show that the radiation entropy is approximately given by twice the entropy of the black hole. And so then you would find, okay, this gives you the so-called island curve, which is always like this. So this shows that we have two different calculations, two different expressions for the radiation entropy. And so the question is, does it follow the Hawking curve or does it follow the island curve? And the answer is it actually follows both, because again, as instructed from the QES formula, is that the radiation entropy is given by the minimum. You take the minimum of the extremized generalized entropy. And so initially, for times less than the page time, you find that the minimum of these two quantities is just the radiation entropy that follows the Hawking curve. And then after the page time, you find that the minimum is given by twice the black hole entropy. And so then together, the Hawking curve and the island curve give you the page curve. So that essentially, that is the application of our setup. This was essentially worked out already back in 2019 by Maldacena and Almiri and others, in other contexts as well, not just ADS2 black holes, but also for dynamical black holes and higher dimensional ADS black holes, and also two-dimensional flat space black holes. But the point is almost all those calculations, they do not include backreaction. They did not solve the fall backreaction problem. What's interesting is that even though we solved the backreaction, our solution is entirely consistent with what they found. And so that suggests that the backreaction, at least in this particular context, didn't change anything. And the calculational reason is because really the only major effect is that when you include backreaction, the dilaton is only shifted by a constant. And so when you extremize the gravitational entropy, it doesn't change anything. Now the real meat and the excitement that happened last year was that it was claimed or argued that there could be a derivation of the QES formula, or really a derivation of the island formula. This was done using the so-called replica trick, which is essentially a way of calculating what's called the reigning entropy using a on-shell Euclidean path integral analysis. And they found that some unseen particular solutions or geometries to the Euclidean gravity problem, known as replica wormholes, are actually the dominant saddles to the path integral, and these replica wormholes are the quantities that give rise to the island curve. And so this derivation was originally done for the ADS2 eternal black holes, but also more recently to the dynamical ADS2 black holes. But the derivation of the island formula has not been achieved for any other system. It's only been done for those two contexts. And in our paper, what we're arguing is that we are claiming that we can derive the QES formula, hopefully both Hawking and island saddles, for first the eternal ADS black hole, and we're doing it working in the microcanonical ensemble. So the way we're doing it is we define the density of states in terms of the microcanonical path integral, where you can show that the microcanonical action of the semi-classical JT action is exactly equal to the generalized entropy up to a sign. So then what happens is minimizing of the microcanonical action, which is equivalent to finding the dominant saddles of your system, is identified with extremizing the generalized entropy with respect to the quantum extremal surface. So that gives you the extremizing and the minimization contributions in the QES formula. And what's great is that this formalism applies to, or this technique applies to flat space theories in 2D. This is one thing we're working on as well. But also this description of the microcanonical path integral has also been worked out for higher dimensional models of gravity and other theories of gravity as well. So the hope is, in principle, though we have no calculations to show this, in principle, this method would be able to describe or derive a QES formula for these other gravitational systems as well. But the problem is, I say the weak point, which may be why some people won't find it interesting, is that it seems that you won't be able to apply this microcanonical setup to dynamical black holes, which are the real interesting systems. But with that, thank you again for your attention, and thank you again for having me. It's been an honor, and I'll take any more questions that you may have. Thank you, Jesse, for the clap.
Thank you. Thanks for a nice talk. I learned a lot. Just there's so much information to digest.
Yeah. Yes. Sorry.
Yeah. No. Any questions from the audience? So
Don't
do I
be shy.
understand? Oh, sorry.
No, go ahead.
Do I understand correctly that this analysis is based on the assumption that the chi field lives in the Hartle-Hawking state?
Yeah. So so you can, right. So there's two things going on. So this entire analysis that I was doing here with thermodynamics, that's working in the Hartle-Hawking state, and that's because the Hartle-Hawking state is a thermal state. You could actually solve the problem of backreaction. Like, suppose you're not interested in thermodynamics at all. You could solve the problem of backreaction with respect to some other vacuum state, like the Boole state. And then you can compute all these various quantities, but they don't have the same interpretation anymore. Like you can actually work out what the Wald entropy is for a Boole state, but it will not be interpreted as a thermodynamic entropy. And if you try to interpret it as thermodynamic entropy, you run into problems.
But would they have some physical meaning?
It's unclear. Because what happens is, so with the Boole state, you'll find that the gravitational entropy which is evaluated at the horizon, actually just diverges to negative infinity. So it's unclear what it means.
I see.
And so really, when you want to have a thermodynamic interpretation, you have to be working with respect to thermal states.
Yeah.
And so that's why you're interested in the Hartle-Hawking state.
I see. Thanks. Have more questions from the audience?
Is Mine not going to speak?
Mine is probably just doing something. Who knows?
No, I'm here.
He's drinking his frappuccino.
Okay, if no, then let's.
Oh wait,
thank
other
Andy.
questions? Hey, there might be questions in the chat. Hang on. Oh no. It's just Minock thinking.
Yeah.
Yeah. Thank you.
Yeah, that's
Thanks a
you
lot
again.
from the all of us who attended the seminar. So
Yeah, no,
Logan,
thanks for changing
Billy,
the time so
Tucker,
all you
and
guys
Max.
could come.
Oh yeah, it's 10 o'clock. It's 10 p.m. right?
No,
Yeah.
it's 9 p.m. for me.
Oh, okay.
Yeah, no, I was an hour off when I first thought of this. But yeah.
Oh, you're in daylight savings right now? Are you in daylight?
Are we? I don't know. I have no idea, to be honest. I've because of lockdown, and the time doesn't matter anymore to me. I mean, I work with people in the US and I work with people in other countries over here. So my computer is in AZ time. So that, like, I still have it in AZ time. So I know what Minock is up to.
Man, it's been a year. It's been a year.
I know. But it helps me keep track of what's going on with my colleagues in the US.
Oh my God. Okay.
I think my phone's also in Phoenix time. Anyways.
Bye, Andy. I have a meeting, so I'll leave.
Yeah, no, yeah. Thank you. Thanks for coming, everyone.
All right.
Yeah,
Bye,
thank you,
Andy.
Andy.
Bye.
Bye.
Bye.